Lecture 17, Self-Stabilization. Preface, recap of previous lecture. In previous lecture we have discussed about message ordering, group communication and application level multicast algorithms. Content of this lecture: in this lecture we will discuss the concept of self-stabilization, related issues in the design of self-stabilizing distributed algorithms and systems, and Dijkstra's self-stabilizing token ring system. Introduction. Concept of self-stabilization. The idea of self-stabilization in distributed computing was first proposed by Dijkstra in 1974. The concept of self-stabilization is that regardless of its initial state, the system is guaranteed to converge to a legitimate state in a bounded amount of time by itself without any outside intervention. So, the non-self-stabilizing system may never reach the legitimate state, or it may reach a legitimate state only temporarily. The main complication in designing self-stabilizing distributed system is that nodes do not have the global memory that they can access instantaneously. Each node must make decision based on the local knowledge available to it, and actions of all the nodes must achieve the global objective. The definition of legitimate and illegitimate state depends upon the particular application. Generally, all illegitimate states are defined to be those states which are not legitimate. Dijkstra also gave an example of the concept of self-stabilization using self-stabilizing token ring system, that is called Dijkstra's self-stabilizing token ring system. So, for any token ring, when there are multiple tokens or there is no token, then such a global state are known as illegitimate state. When we consider the distributed systems, where a large number of systems are widely distributed and communicate with each other using message passing or shared memory approach, there is a possibility of these systems to go into an illegitimate state. For example, if a message is lost, the concept of self-stabilization can help us recover from such situation in a distributed system. So, again, before going ahead, so Dijkstra gave an example of a token ring system. In a token ring system, you know that only one token is called privilege which circulates, and if it circulates, then it is legitimate state. In the system. Now, in contrast to this, if this particular token ring has two privileges or two tokens or more than one token, or it does not have a token at all, or a token is lost, this particular situation is illegitimate state as far as this definition is concerned. So, this particular state, which is illegitimate state, if it goes to a legitimate state automatically without external intervention, then it is called a self-stabilizing system. If it is a token ring system, then it is called self-stabilizing token ring system. In a distributed systems, you are seeing that lot of processors are connected through the communication network and they exchange through the message communication. So, there is a possibility that nodes may fail down or the messages may lost. Obviously, these conditions will basically lead to a illegitimate state in the distributed system. How the self-stabilizing distributed system will recover automatically to a legitimate state is basically a design issue which Dijkstra has opened through this particular system, that is called a self-stabilizing system. So, the concept of self-stabilizing is very useful to understand about the self-stabilizing system and the design for different distributed systems based on this particular concept. So, let us explain the concept of self-stabilization using an example. Let us take a group of children and ask them to stand in a circle. So, after a few minutes, you will see almost almost a perfect circle without having to take any further action. In addition, you will also discover that the shape of this circle is stable, at least until you ask the children to disperse. If you force one of the children out of this particular position, the others will move accordingly and they will form a bigger circle. So, keeping the shape of the circle unchanged in all the cases. So, in this example, the group of children build a self-stabilizing circle. So, if something goes wrong with the circle, they are able to rebuild the circle by themselves without any external intervention. So, we have seen an example of a self-stabilizing circle and by a group of children, and the legitimate state and illegitimate state, all these things we have seen. So, this particular example motivates us to understand about self-stabilization in different type of systems, especially in a distributed system. Now, the time required for stabilization varies from experiment to experiment depending on the random or the initial position. However, if the field size is limited, in the case of the children building a circle is limited, this particular time will be bounded. The algorithm does not define the position of the circle in the field, so it will not always be the same. The position of each child relative to each other will also vary. So, there are several factors, meaning to say that particular factors are going to basically take how much time the system is going to stabilize. So, the self-stabilization principle applies to any system built on a significant number of components which are evolving independently from one another, but which are cooperating or competing to achieve a common goal. And example is the distributed system. So, this applies in particular to a large distributed systems which tend to result from integration of many subsystems and components developed separately at the earlier times or by different people. So, in this lecture we will first present the system model of distributed system and present the definitions of self-stabilization. Next, we will discuss Dijkstra's seminal work and use it to motivate the topic, and then we will discuss the issue arising from Dijkstra's original presentation as well as several related issues in the design of self-stabilizing algorithms and systems. Let us see the system model. The term distributed system is used to describe the set of computers that communicate over the network. Variants of distributed systems have familiar fundamental coordination requirements among communicating entities, whether they are computer processor or processes. Thus, an abstract model that ignores the specific setting and captures an important characteristics of a distributed system is usually used. In a distributed system, each computer runs a program composed of executable statements. Each execution changes the content of the computer's logical memory. An abstract way to model a computer that executes a program is to use state machine model. A distributed system model comprises of n state machines called processors that communicate with each other. So, each processor is nothing but a state machine. So, each processor is nothing but a state machine, and these particular processors will communicate with each other also, and these processor will make a transition among these states. So, the example here is basically comprising a set of n state machines called processors which were communicating with each other, usually denoted ith processor denoted by Pi. The neighbor of processor are the processors. So, here we are calling it as the left and the right neighbors, and the system we are considering to be in a anti-clockwise directed. A processor can directly communicate with its neighbors. A distributed system can be conveniently represented by a graph in which each processor is represented by a node and every pair of neighboring nodes are connected by a link that I have shown in the figure. The communication between neighboring processors can be carried out either by message passing or shared memory. Communication by writing in and reading from the shared memory usually fits the system with processors that are geographically close together, such as multiprocessor computers. Message passing distributed model fits both processors that are located close to each other as well as they are widely geographically distributed and they are connected over a network. In the message passing model, neighbors communicate by sending and receiving messages. Message passing communication model should contain a queue and which is represented as Qij for the messages from Pi to Pj. It is convenient to identify the state of a computer or a distributed system at a given time, so that no additional information about the past of the computation is needed in order to predict the future behavior of the computer or a distributed system. A full description of a message passing distributed system at a particular time consists of the state of every processor and content of every queue. The term configuration or a configuration is used such that such a description configuration is denoted by a set, that is C, which contains the states where Si is the state of a Pi and Qij where I is not equal to j is the state of a queue, that is the message is sent by Pi to Pj but not yet received. The behavior of a system consists of a set of states, a transition relation between those states and a set of fairness criteria on the transition relation. The system is usually modeled as the graph of processing elements where the edges between the elements model the unidirectional or bidirectional communication links that I have already explained. Let capital N be the upper bound on n, that is the number of nodes in the system. The communication network is usually restricted to the neighbors of the particular node. So, here the diameter and the big delta denotes the upper bound on that diameter. Network is static if the topology remains fixed, dynamic if the links and networks can go down and recover later on. So, self-stabilization is guaranteed eventually in spite of all the faults. Shared memory model is basically we are not going to consider. Two neighboring nodes have an access to a common data structure or variable is not possible in distributed systems. So, the algorithms are modeled as the state machine performing the sequence of steps. A step consists of reading input and the local state and then performing the state transition and writing output. Communication can be by exchanging messages over the communication channel. So, a related characteristic of a system model is the execution semantics. If the self-stabilization, this has encapsulated within the notion of scheduler or a daemon, also called daemon. Under a central daemon, at most one processing element is allowed to take a step at a point of time. So, we will see that these particular assumptions are basically well defined for a particular self-stabilizing system. Definition of self-stabilization. We have seen an informal definition of a self-stabilization at the beginning. Formally, we define self-stabilization for a system S with respect to a predicate P over its set of global states, where P is intended to identify its correct execution. So, the state satisfying the predicate P is called the legitimate state, and those not satisfying the predicate P are called illegitimate state. We use the term safe and unsafe interchangeably with the legitimate and illegitimate respectively. So, a system S is self-stabilizing with respect to the predicate P if it satisfies the following two properties, which are most important. So, the first property is called the closure property, says that P is closed under the execution of S. That is, once P is established in S, it cannot be falsified. Second one is called convergence. Starting from an arbitrary global state, the predicate system defined by P, that is called S, is guaranteed to reach a global state satisfying P within a finite state of transitions. So the closure and convergence are two important properties in the self-stabilization. So we define the self-stabilization or stabilization for a system S, and self-stabilization is basically a part of the stabilization. So self-stabilization is a special case of stabilization. Now then, there is a reachable set. Often when the programmer writes a program, he/she does not have a particular definition of a safe and unsafe states in mind, but develops a program to function from a particular set of start states. Such situation, it is reasonable to define as states those states that are reachable under normal program execution from the set of legitimate start states. These are referred to as reachable sets. Transient failures. A transient failure is temporary or short-lived and does not persist. A transient failure may be caused by corruption of local state processes or by corruption of channel or shared memory. Transient failures may change the state of a system but not its behavior. Issues in design of self-stabilization algorithms. A distributed system comprises of many individual units, and many issues arise in the design of self-stabilization algorithms in distributed systems. Some of the main issues are number of states in which each of the individual unit in a distributed system, uniform and non-uniform algorithms, central and distributed daemon, reducing the number of states in a token ring, shared memory models, mutual exclusion, and cost of self-stabilization. The mentioned issues can be explained with the help of Dijkstra's landmark self-stabilizing token ring system. So his token ring system consisted of set of n finite state machine connected in a form of a ring. I told you previously, and he defines the privilege of a machine to be the ability to change its state. So that particular node, which is called a privileged node, has the ability to change its state, and Dijkstra assumes initially that there is only one privilege at a particular point of time, but later on it changed the model, and we are going to see both models in this part of the discussion. So this ability is based on the Boolean predicate that consists of the current state and the state of its neighbor. So when a machine has a privilege, it is able to change its current state, which is referred to as a move. So furthermore, when multiple machines enjoy a privilege at the same time, the choice of the machine that is entitled to make a move is made by a central daemon, which arbitrarily decides which privileged machine will make a move. So these are the important concepts which I will again highlight before going ahead. So first thing is, in a given self-stabilizing in a system, there must be some set of privileges, and these privileges are subject to the Boolean predicate, and it will change the state from illegitimate state to the legitimate state following two rules which we have seen, closure and the convergence. So furthermore, when multiple machines they enjoy more than one machines having a privilege at the same point of time, then the central daemon will come, and this will decide among many privileges, one of these privileges will be activated or will be allowed to make a move at particular point of time. A legitimate state must satisfy the following constraints. There must be at least one privilege in the system, that is liveness or no deadlock. Every move from legal state must again put the system into a legal state. So from one legal state, the system will make a move and go to another legal move, that is called a closure property. So during an infinite execution, each machine should enjoy a privilege an infinite number of times. So that is the no starvation condition. So, given any two legal states, there is a series of moves that change one legal state to another, that is called the reachability. So, Dijkstra considered a legitimate or a legal state as one which exactly one machine enjoys the privilege, as I told you that only one privilege is initially considered by Dijkstra. This corresponds to a form of mutual exclusion because privilege process is the only process that is allowed in the critical section. Once the process leaves the critical section, it passes the privilege to the other nodes. The number of states in each of the individual units. So, the number of states that each machine must have for the self-stabilization is an important issue. Not only important issue, but it's a design issue as well. So, in the previously we have seen how to minimize this number of states, and that will be the one of the most important design issue in self-stabilization. So, Dijkstra offered three solutions for a directed ring with n machines, each having k states. So, the three solutions, wherein the first one assumes that the number of states is same as n or more than that, so greater than or equal to n. The second solution assumes the number of states is equal to 4, and then we will see that k is equal to 3. That means the Ghosh has proved later on that with the number of states is equal to 3, it is possible to design a self-stabilizing system. So, Ghosh proved that minimum of 3 states is required in a self-stabilizing ring. So, in all three algorithms, Dijkstra assumed the existence of at least one exceptional machine that behaved differently from others. Let us see the first solution, where the number of states is assumed to be greater than or equal to the number of nodes or the processors in the system. So, this is very loose bound on the number of states. So, for any machine we use the symbols S, L, R. S means its own state, and L is the state of its left neighbor, and R is the state of its right neighbor on the ring respectively. So, meaning to say that if this is the ring and this is the state, so if this is the current state, so this is S, its left neighbor is L and its right neighbor is R respectively. Now, Dijkstra assume one machine which is called an exceptional machine. The code of exceptional machine is like this: if L is equal to S, that is the state of left is equal to state of the current state, then S, the state of S or the current state will be modified as S plus 1 mod k. The other machines which are not an exceptional machine, so there if the state that is left is not equal to the current state, then the current state will be same as the left state. Now, in this algorithm, except the exceptional machine 0, all other machines follow the same algorithm. In the ring topology, each machine compares its state with the state of its the anti-clockwise neighbor, and if they are not same, it updates its state to be the same as that of its anti-clockwise neighbor. So, if there are n machines and each of them is initially at a random state drawn from possible set of states, then all machines except the exceptional machine, that is machine 0, whose states are not the same as their anti-clockwise neighbor, are said to be privileged, and there is a central daemon which will decide which among those privileged machine will be allowed by the system to make a move. Suppose machine 6 in a system which has the number of nodes or more than 6 makes the first move. it is obvious that its state is not the same as that of the machine 5, and hence it had the privilege to make the move and finally sets its state to be the same as that of machine 5. Now machine 6 loses the privilege as its state is same as that of its anti-clockwise neighbor machine. So let us see the example of this particular description right over here before we take it. So if this machine 6 is going to make a move, so its neighbor is 5, which is at the left. If it is going to make a move, then the current state of 6 is not equal to current state of 5, so it will change the state accordingly. Let us say that the state of 5 is, let us say, 0 and the state of 6 is 1. So now the state of 6 will be changed to 0. So finally sets the state to be the same as that of machine 6, that we have done here. Now machine 6 loses its privilege as its state is same as that of anti-clockwise neighbor 5, that I have explained. Now next, suppose machine 7, whose state is different from the state of machine 6, let us say its state is 1, is given the privilege. It is having a privilege. Why? Because its left neighbor is not same as its current state, that is 0 and 1, they are different. So hence it will be a privileged. So it results in making the state of the machine 7 as that of machine number 6. So it will become 0 in this case. Now machine 5, 6, 7, they are in the same state, that is equal to 0. In the above example. So eventually, if we see the progress, all the machines eventually will basically make a transition and will have the same state, that is 0. Then what will happen? So eventually all the machines will be in the same state in the similar manner. So at this point only an exceptional machine, that is machine 0, will be the privileged, as its condition L is equal to S will be satisfied. So there exists a machine 0 whose left and right, whose left and the current state both are same here. Then according to the exceptional machine code, if they are same, then they have to make a move, and its state is the same as that of anti-clockwise neighbor. Now there exists only one privilege or a token in the system, that is machine 0 makes a move and change its state from S to S plus 1 mod k. So that machine in that case 0 will make a move and its state will become 1 according to this particular formula, and this will trigger the next state which is left, which is 0. So they are not same and so on. This particular way the token circulates or the move circulates around the ring. So this will make the next machine 1, here as I shown you, is privileged as its state is not same as in the anti-clockwise neighbor, that is here. Thus it can be interpreted as a token currently with the machine 1. So machine 1 will change it to 1 and so on. So now it will go to the 2, 2 will is having 0, it will become a privileged and so on. So the moves will move in this manner, the clockwise way, although the ring is basically identified in a anti-clockwise manner. So machine 1, as per the algorithm, changes state to the same state of that machine 0 and move to the machine 2 and so on. So this is a simple algorithm, but requires the number of states which depends on the size of the ring, which may be awkward for some applications. So I explained you that if let us say node 6 is going to make a move, move means if it is a privileged, and privileged means its left is not equal to the current state, that is S. So, let us assume that it is having 0, state is 0 and this state is 1. So, they are not equal. If they are not equal, then S will be assigned to L. So, that means 1 will be changed to 0 and both will be now having the same state. Now, let us assume 7, which is having the state 1. Now, these two states are not same. So, this will become privileged. This is no longer privileged because its left is same as the current state. So, this will become a privileged. So, if it is privileged, then again it will set its state to the same as the left one. So, that means here S will be assigned to the left is 0. So, this way eventually all the nodes will be able to change the state and that is the same state, but there will be an exception. So, according to the convention there is a non or there is an exceptional node. So, this let us say 0 is an exceptional node, and exceptional node says that the code of a exceptional node says that if this particular left S is equal to left, S is not equal to left, then basically this will change to 1. So, exceptional machine says that if both are equal, then S will be incremented by 1. So, if both are equal to 1, so it will be changed to 1 in this case. Now, this is a non-exceptional node. A non-exceptional node will see that its left neighbor is 1. So, it is going to change and it will change its state and it is no longer privileged. So, the privilege will be here. Why? Because both S is not equal to L and so on. So, just see that all the states will now being rotated and changed to 1, and again finally come back and found out that this is an exceptional node and it is now privileged, and it will change again from 1 to 0 and so on. So, keeps on rotating the token in this particular manner, and this is the legitimate state. So, you just see that whenever there is a move, it goes from one legitimate state to another legitimate state according to the programs which are defined. Now, there is another solution which says that the previous solution has considered that k is greater than or equal to n. That means the number of states are too much depending upon the number of nodes which are there in the system. Now, the second solution says that let us assume k is equal to 3. So, the states for the k is equal to 3 will be 0, 1 and 2, which are assigned to a 3-state machine to every node of a system. So, in the first algorithm there is only one exceptional machine. So, by reducing the number of states from n to 3, now the number of privileged nodes also will be increased from 1 to 2 over here. So, there will be 2 machines which are privileged machine or exceptional machine code. So, these are called machine 0, and which is machine 0 is also called a bottom machine. So, here if you see a ring structure, let us see that this is a 0. So, it is a bottom machine and its number is 0, and here this will be a machine number n minus 1 and it is called a top machine, and they are 2 machines which are exceptional machines. So, let us see the program in this particular problem setting where k is equal to 3. So the bottom machine, as I explained you, will have this kind of code. If s plus 1 mod 3 is equal to r means the neighbor on the right side, then s is equal to s minus 1 mod 3, and the top machine, which is the machine number n minus 1, if left neighbor is equal to right neighbor and the left plus 1 mod 3 is not equal to the current state of the machine, then current of the state of the machine is increment is basically the left plus 1, and all other machines in this case, either of these two rules are applied, whichever is correct is being applicable. If the current state plus 1 is equal to the left neighbor state, then state will be same as the left neighbor. Otherwise, if s plus 1 mod 3 is equal to the right, then basically s is equal to right. So in this algorithm, the bottom machine 0 behaves as follows, that we have seen. Thus the state of the bottom machine depends upon the current state and the state of its right neighbor. The condition s plus 1 mod 3 covers 3 possible states for s is equal to 0, 1 and 2. Thus we have s plus 1 mod 3 is equal to 1, 2 and 0. These results in the following 3 possibilities. So when s plus 1 mod 3 is equal to 1, when s plus 3 mod 3 is equal to 2, and when it is 3 and it is same as r, then s will be 0, 1 and 2. So let us see that when s is equal to 0, here if you see s is equal to 0 and r is equal to 1, then the state of s will be changed to s minus 1, that is 2. When s is equal to 1 here and r is equal to 2, then s will be changed to 0, because s minus 1, 1 minus 1 will become 0. Similarly, in this condition s minus 1 means 1. So this particular case is considered for the bottom machine, that is machine number 0 will behave in this manner. Similarly, we can see about the top machine, that is the machine number n minus 1 will behave according to this rule. So the top machine depends upon both its left and right neighbors. The condition specifies that the left neighbor L and the right neighbor R should be in the same state here, and L plus 1 mod 3 should not be equal to S, the other condition connected by an AND. Note that L plus 1 mod 3 is 1, 2 and 0 when L is equal to 0, 1 and 2 respectively. Thus the state of the top machine will be assigned to 0, and it will be assigned to 1, and it will be assigned to 2, from 1, 2 and 0 according to this particular rule. Now all other machines behave as follows, as I explained you. While finding out the states of the other machines, machine 1 and machine 2, let us, for example, below we first compare the state with its left. So when s is equal to 0 and L is equal to 1, so s is equal to 0, this will become 1, and L is also 1, both are equal, then s will be assigned to L. If it is not assigned to L, then basically the second rule will be basically considered, and so on. So if the given conditions are not satisfied, then the machine compares its state with its right neighbor, that I explained in the previous example. So the same execution of Dijkstra's 3-state algorithm for a ring of 4 processors is shown in the next table. Machine 0 is the bottom machine and machine 3 is the top machine. The last column of the table gives the number of machines chosen to make a move. Initially 3 privileges exist in the machine. The number of privileges decreases, only 1 privilege is in the left. So initially you see that there are 3 privileged machines are there, and then it will be moved to 2 privileges, and finally 1 privilege at a time onwards. Now, as far as the machine is concerned, so let us go back again. So machine 0 is the bottom machine and machine 3 is the top machine. So this is the bottom machine and machine 3 is the top machine. These two codes are different and these are the other machines which will follow a different code. So on the last column here you can see that the machine to make a move is basically mentioned over here. That means these are the privileged machines. If more than one privileges are there, then central domain will select one and it is allowed to make a move. So here out of 2, this is allowed to make a move. In all other cases, the same machines, same privileged node will be allowed to make a move in this particular diagram. Observations. So we can make the following observations. There are no deadlocks in any state. The closure property is satisfied, no starvation is also satisfied, reachability is also there. So all 4 constraints for a legitimate state are satisfied, so the system is stabilized. Few other works in the field of self-stabilization are mentioned here for further reading. Conclusion. Self-stabilization has been used in many areas and the areas of study continues to grow. Algorithms have been developed using central and distributed daemons and uniform and non-uniform algorithms. The algorithms that assume the central daemon can usually be easily extended to support distributed daemon. So these algorithms are still useful when applied to the distributed system. In this lecture, we have discussed the concept of self-stabilization, system model, related issues in the design of self-stabilizing algorithms and systems, and also discussed Dijkstra's self-stabilizing token ring system. Thank you.